I'd like to introduce Dr. Katherine Perdue as our keynote speaker, with a PhD in Biomedical Engineering from Dartmouth. Katherine's expertise is very expansive throughout her professional career. She's built up experience in research and neuroscience study. Now at Kernel as a research scientist, Katherine has worked on neuroimaging, system characterization, optimization, configuration, and much more. And so I'll pass that off to you.
Okay, is that good? Good, okay, yes. So yeah, thank you so much for having me. It's been really interesting and inspiring to see the talks and to talk to you all. So yeah, thank you for the invitation. Yes, I wanted to talk just for a second about like how I have this position and how I got to Kernel. So my undergrad degree is actually in physics. I was really interested in experimental physics, and then from there I went to is kind of weak, like cool to understand this concept there. I just wanted to do that. So I was in development of technology, so I decided at that time, although I still remain kind of interested in both. During my PhD, I specialized in optical brain imaging, which is what I'm going to talk about through here. And then from there, I went on to do a postdoc in cognitive neuroscience. There in that lab, I worked on neurodevelopment, which is a really common application of optical imaging technologies. We did a bunch of studies with babies, kids, trying to figure out how we can understand the brains of small wiggly creatures. So that was, again, really an interesting development or an interesting opportunity. And I really enjoyed the ability to look or to kind of apply the technology to this really interesting use case. So from there, I moved on to Kernel. I've been at Kernel for around 3 years. So I've been doing optical brain imaging for over 10 years, and I've been at Kernel for over 3. And at Kernel, Kernel is a startup, and we have been developing our technology over that time, even before I joined. And in my role, I have been able to use all of my backgrounds. I currently lead our neuro research programs. So me and my team, our job is to design and execute our neuroscience studies that show how our technology can be used. Our technology is a little bit sci-fi. It can be a little bit difficult sometimes, probably not for this crowd. You guys might have lots of ideas for how to use it, but it can be hard for some people to understand how technology like this could be used. So the role of our team is really to design studies and show how our technology can be used. And that's what I'm going to talk about today. I'll talk about optical imaging in general, but I'll also talk about our ideas at Kernel about how this technology can be used and the steps that we're taking to kind of develop these applications. Okay, oh, there we go. So first, if you don't know about Kernel, we are a neurotech startup that is based in Los Angeles. So I'm talking to you from Los Angeles in our office. It was founded in 2016, actually as an invasive company. But from there, in around 2018, that's when our optical brain imaging program started. So yeah, we are full stack. So that means that we do everything in-house, from chip design to electrical engineering, mechanical engineering, all software is in-house, and all neuroscience is in-house, our IRB approved neuroscience application studies. So we really do everything, and it's a great environment. There's like 100 of us here, something like that. And it's amazing to be able to work with so many experts, so many dedicated people, and to really, be able to accelerate the technology because we're all dedicated to this particular goal of, making neuroimaging accessible, maybe to people who don't want to solder things, although that I also like soldering things, that's fine. But our goal is to aim towards consumer neuroscience. We're always looking for new team members, so please check out our website and see if there's anything that might work for you. It's a great place to work. So I wanted to start off optical brain imaging, just give a brief overview of what it is and how it works. So the basic idea of optical brain imaging is that you shine some light into some body tissue. In our case, it's the brain or the head. And then you look at the light that comes out some distance away, and that tells you something about the stuff that's happening between that source and that detector. So here, this is a model. So if you have some external surface here, like scalp, you have some light that goes in, those photons, they all bounce around, and just by chance, some will bounce into the brain and then come back out and be able to be detected. So this is the basis of most optical imaging, or all optical imaging. The optical imaging that's most commonly done puts in a continuous stream of light. So it's called continuous wave or CW near systems. NIRS is for near infrared light. So that is the wavelength of light we use. If you've ever, it's almost Halloween, if you've ever put a flashlight on your hand or on your face and you see it glow red, that's because red light travels particularly far through body tissue. So that's the light wavelength that we use. Okay, so our light is traveling in, it's interacting with this tissue, and some light is detected. For our type of system, it's a totally novel design or new type of, it's not a new type of imaging. It's been used for a long time, but the form factor, the way that we're able to implement it, is very novel. So the basics or the physics behind it is that instead of sending in light all of the time, we only send in a very narrow pulse of light. So we know that all the photons are hitting our surface at around the same time. And then we look at the time distribution. So this is time over here, and we look at that time distribution of the arrival times. So we have a much richer source of information here because we're able to tell, so the photons that are arriving first, they went probably pretty shallow. And as we get further into this histogram, we are on average seeing photons that went deeper into the head. So this is giving us a very rich source of information. It turns out that people can use the shape of this histogram to tell you something about the absolute properties of this tissue instead of just looking at relative changes like we would with CW systems. So this is the technology that we've been, it's called time domain functional near infrared spectroscopy, TDF NIRS. And our helmet also includes 6 channels of EEG. So the other thing that I want to bring up here is the signal that we're looking at. So we're interested primarily in functional changes or brain activity changes. And that brain activity change is related to hemodynamics or blood oxygen levels. So we're not looking directly at the electrical activity of the neurons. Instead, we're looking at the hemodynamic responses. So those changes in blood oxygen levels. So that means that the way that I used to explain it to the kids in our studies is that we're looking at how hard your brain is working in a particular area. If your brain's working hard, it uses more oxygen. There's some additional complication in there, but that's the general idea of of how the technology works and what we're measuring. Okay. So as I mentioned, this is not, the technology itself is not new. It's been around for a while, but it has been very large. So this is an example of a state-of-the-art academic system, actually made by a friend of mine. It's really cool. And this is an example of one kind of implementation of this type of device. And what you see, like this down here is a computer. So this is 2 gigantic racks of equipment. And all of this equipment is for a system that has 1 laser and 4 detectors. It's got all these fibers that are taking the light to the head and getting the light from the head back to the detectors. It's a very large, slightly clunky system, even though it's quite useful. So comparing that to what we've developed at Kernel, so this is the system that we have. image that I showed you before was it flipped upside down. This is what it looks like from the outside. So this is, and there's no extra, nothing goes with this except for there's a single USB cable that comes out and plugs into a computer. So that is all there is to it. And then in here, what we have is 52 modules. Each module has a single source. Well, there's 2 different wavelengths of light, but the single source location, and then 6 detectors. So we have over 312 detectors in this helmet for over 500 channels of data coming in. So this is like wearing, I don't know how many, over 52 of these things all on your head. We've managed to miniaturize the technology and really revolutionize how this kind of technology can be used. So this is our first, well, it's not, this is a product that is shipping. It's also, we have partners that have the system. I have, as our neuro team in-house, we have many of these systems that we work on or use for our neuroscience studies. So this is a real device that we are using and expanding the use of and trying to understand like what are we learning when we have this much data coming off. Oh, the other thing that I want to mention is that our sampling frequency is also quite high. So our native sampling frequency, we get histograms, so those light measurements off every 200 hertz. So that is very fast compared to the hemodynamic signal, which is great. And the thing that it allows us to do, so we do some time multiplexing. So we turn on the modules in a pattern, some are on, some are off, so that we don't get crosstalk between the detectors. So that takes our overall sampling frequency down to around 10 hertz, which is still perfectly adequate to capture our hemodynamics. But really, this is a very fast system where we have good temporal resolution along with the spatial resolution that we're getting from our optical signal. Okay, I wanted to show just a little bit more of the details. So the way that our system is working, so this is showing the way that we are able to miniaturize our device is by this chip design. So we have single, our source in here with our 2 different laser wavelengths, and then all the detectors are just in chips that are in this module. So the detectors themselves are able to be placed, well, they're not technically touching the head, but they're able to be placed in those modules that are held onto the head. And our overall design is, it has the sources, detectors, and then it has these spring-loaded light pipes. By light pipes, I really just, they're pieces of plastic that guide the light. So it's able to be put on the skin. It conforms to your head, and because it's spring-loaded, all those light pipes are touching and able to conduct the light to the scalp and take it and measure it. So our modular design, there are 52 modules, as I said, over all of these plates, yes, the total number of modules is 52. So we're able to have good coverage over the whole head with this incredibly rich signal that's coming out of our detectors. Okay, so I wanted to show a little bit of what some of our data looks like, or an example. The first, this is for any NIRS people in the audience, but I wanted to show that even though it's a time domain signal, so usually the time domain temporal resolution is very slow, maybe a hertz, maybe slower than a hertz. So for us, we actually are able to see good enough temporal resolution to see this cardiac artifact, even with our time domain system. So we're able to record our data really quickly. And this looks like, if you didn't know any better, you might think that this was a continuous wave system or a much simpler system, but really there is a rich amount of information that's going into each of these time points. So this is just, we think about spatial mapping with this kind of system to some extent. So this is just showing some of our classic validation task results. So we have finger tapping, which is a really classic validation task. If you move your left hand, you expect to see activation in your right motor cortex. That's what we see. We did a Stroop task. So in that, the Stroop is a color word task. So there are colors of words, and sometimes the words and colors match and sometimes they don't match, and your role as a participant or someone who's doing this task is to always say the color of the word. So if they match, it's pretty easy. If they don't match, it's hard. So we see some additional prefrontal cortex activity when you have to do the hard version of that task versus the easy version. And then this is an example of some of our modeling efforts. So just from a single participant, are we able, again, it's this finger tapping, left minus right contrast. We see good localization in the motor cortex like we expect. So this is the kind of, this is using the flow device like it's a classic neuroscience tool, but we wanted to start there. Before we try to do anything that's too sci-fi, we gotta make sure that our science results look like we expect. And it seems like they do, so that is great news. Okay, so from there, I wanted to talk a little bit about what we think it will take for individuals to be able to record and understand their own brains. And these kinds of individuals, I'm thinking about it from the perspective of someone who might not have any neuroscience training or engineering training or anything at all. Like, how do we get to the point where it's not hard for people to learn how to understand their own brain, or it doesn't take several decades of training and knowledge and soldering skills? Okay, so I think there are many steps that will be really difficult. Each of these steps is very difficult, but here's how I break it down, or how I would think about how we would be able to get to this vision where we're able to have people, we call it the self-checkout model, where people are able to put on the kernel flow helmet, all of this very complex engineering and neuroscience that goes into it, to just put it on, be able to look at their phone and be able to understand their own brain. So the one thing, or the first thing that we're interested in, or that will need to happen, is that we'll have to have very low cost of hardware. So the system that we have now, the kernel flow system, and what we ship, it is not low cost. It's still in the range where you're thinking about it, maybe not exactly like it is medical equipment, but still like it's a research grade tool, or we're thinking about it as with people who, for researchers, or that's like kind of the sort of people that would be able to afford this kind of equipment. But even though our current system is it is not at consumer level yet, we are developing our systems with the eye towards scaling towards commercial systems. So we are using scalable technology. We're thinking about, we need to be able to manufacture like thousands or millions of devices. So that's what goes into our design process. We're also interested in having a comfortable and adjustable headset. So it's really important. If something's not comfortable, it's not going to get worn. And actually, in my prior life, that was one of the most difficult problems to solve, because it wasn't a cool technical problem. Like, you're just trying to fit something on the head and keep it there. I mean, it is a cool or interesting, it's very big challenge to figure out, how do you get something that's as technologically advanced as what we built? How do you get it so that it can sit firmly on a head, so that it's comfortable, so that it fits on everyone's head, and that so you would want to wear it for, I don't know, 30 minutes or an hour, something like that. So we have a whole mechanical engineering team at Kernel that's their whole job, is to work on this problem. So that is really great, but it is a big challenge. Yeah, the next big challenge that we have is thinking about consumer-friendly setup guidance. So this is, again, getting back to the self-checkout. When I worked in academia, I would do all the setup. It required a lot of training to teach people how to set up FNIR systems in order so that they could get good data. And what we work on at Kernel is try to figure out, how do we simplify? Like, I know when I was in academia, I would be looking at the signals and I would be doing some math in my head and figure out, like, okay, this one looks good. Okay, these two channels are not good, so I need to move this part. So how do we get from having to do that to be able to, like, our UI right now just kind of has green lights and red lights, or they're only green, they get more green. but thinking about how can we explain to people how to put on a headset so that it would be reliable each time, so they would get good signal all the time, and not have to have a training process. The next difficult thing that we have to do is figure out how to have fast and automated data processing. Both of these are a big challenge. We have just a ton of data coming off the system. It's really, I think it's almost a gigabyte a minute. It's not quite that, but it's a very large amount of data. We push it up to the cloud so that we can do our processing there. But it's a big challenge for us, is determining how to process all this data quickly. And then the other part of the challenge is automating data processing. There's a lot of, we used to call it like artisanal processing, a lot of tweaking, a lot of, again, this expert knowledge that went into doing FNIRS processing when I was in academia. But if we're thinking about scaling it out like a consumer product, we really need to be able to automate that and make it robust and make sure that it works each time. And the last, small challenge on our goal or our path to this very consumer-friendly neurotech is to have interpretable results. And in some ways, I feel like, well, and all of these are challenges, that interpretable results is also a very big challenge. So for academics, we know academics are very happy if you could say, oh, the dorsolateral prefrontal cortex is more activated in this task versus that task. They're happy with that. I have not found that the general public, they don't really care about that. They don't want to know, like, oh, just this region of my brain is more active. They want to know, what does it mean, right? It totally makes sense. So they want to know, like, maybe that their brain has to work harder during a particular task versus another task, or maybe they're engaging some kind of network for one task versus another task. But again, like getting to this point where we're able to tell someone insight about their own brain that they'll be able to understand without any neuroscience classes, it's a big challenge. And we do work on this. Our internal studies at Kernel, we always show people their brain data and talk to them about it and figure out, oh, what do you think about this? What are you seeing? Does it make sense? And that has been a very enlightening and interesting experience as well. Okay. So once we solve all of those small technical hurdles, we're left with what questions we think people will have about their own brains. So we don't think that at Kernel we will be able to guess every question that people will have about their brains. Instead, these are just some things that we think people, some categories or that we think people might be interested in. So the first type of a question that we think people might have about their brains is I call it the stable brain. So we think some brain measurements might change slowly or be intrinsic to a person. So my favorite example here is to think about empathy. So are we able to determine from brain measurements how strongly someone might feel the emotions of other people? Because we know that there's variability in that between people. It's really hard to kind of talk about or experience, but maybe if we were able to measure the brain directly, we would be able to know. So that's cool. And then the second type of thing that we're interested in, or a type of question that we think people have, I call it like the daily brain. So what do you want to know about your brain today? So for example, like some kind of fitness trackers give a score of readiness for the day. So what would our equivalent, or what would the analogy be for the brain? How could we tell you like how ready your brain is for the day? Okay, so we have done several pilot studies at Kernel, and we have a few more planned. I know I'm running a little short on time here, I think, but our pilot studies have been looking at, one was looking at the variability in sleep, so looking at how natural variability in sleep impacts a few different areas of cognition, including inhibitory control, visuospatial learning, those kinds of things. So we're interested in telling people, all of our studies that we do, most of our studies that we do, we measure the same person repeatedly. So we are interested in figuring out what can we tell a person about their own brain, instead of just like, what can we tell about humans' brains on average? So yes, our first study was about sleep. We have a current study in progress that's looking at how learning to meditate can change the brain. So we have a cohort of people who are learning to meditate over 3 months. It takes a while to learn how to meditate. And we're looking at the impacts on their brain activity while they do attention tasks, as meditation is supposed to help you train and have better control over your attention. The two other areas of interest for us is looking at brain activity during video gaming. We know that gamers are really interested in performance improvement. So we're interested in that as like a way to think about like, how can you play a video game? Can you figure out like what your optimal performance is or how to train better? And then the other one, we just announced that we have a partnership with Cybin. So we're looking at brains during undergoing a psychedelic experience, so under the influence of ketamine, and that's a study that is planned. We haven't started it yet. Okay, so we still have some big questions, like how do we take these very complex brain measurements and condense them down into a score or something that would be robust, so reasonably reliable and understandable? And then the other thing that's on my mind a lot is that how do we make sure that if and when we do see day-to-day variability, that it's related to something interesting, like maybe a person's stress levels, and not something boring, like maybe they didn't quite put the headset on the same way each day. So just thinking about how do we tease out these different sources of variability and validate our measurements. All right, that's the end of my talk. Thank you so much for your time and attention. Obviously, Kernel is a big company, so there's a lot of work from lots of people that went into this. But yes, thank you so much for your time.